This is an example of calorimetry that you will have on your Mastering Physics assignment. So I think I'll just run through the numbers with you, and remember that you have to use the constants that are given in the problem. So this is a situation of ice at -17 being added to hot water, and we want to know how much ice it takes to cool the water off. So let's do our little diagram for the ice. It starts out at -17 degrees Celsius. First, it has to warm up to its melting point. So it has to remain ice, but warm to its melting point. Then it has to melt. And after it's melted, it's still at 0, but now it's water. And then finally, it can warm up to the final temperature of the whole mixture, which is 12. And this is still water. Okay, so that is going to require heat, and that heat is going to come from the hot water. So that's for the ice. And then this is the mass of ice. It's the same mass for the whole time. Now the water, the hot water, it's going to lose heat. So this is a gainer. So this gains heat. And the hot water is a loser. And so it starts at 70 and remains water down to 12. And so this loses heat. And calorimetry says heat lost equals heat gained. Okay, so this warming of ice is mc ice delta T. Melting of ice is mLF for latent heat diffusion. And then warming the water is mc delta T of water. Okay, so 3 different constants up there, and this is mc water delta T. This would be mass of ice, ice, ice. This would be mass of water. Okay, and it's mass of ice that we're after. So let's write this down. Heat lost equals heat gained. Okay, and so we have the mass of the water, C water delta T is equal to mass of ice, C ice delta T plus M ice LF plus M ice C water delta T. Okay, quite a few terms. Now the tricky parts are the delta T's. Remember, if you're going to do heat lost equals heat gained, all delta T's are positive. So hot minus cold. So this delta T would be 70 minus 12 for the water. This delta T would be 0 minus -17. So that's the amount that the ice has to warm up before it gets to its melting point. And this delta T would be 12 minus 0. That's how much I call it the ice water, or the melted ice, has to warm up from 0 to 12. Okay, so if we solve for the mass of ice in this equation, mass of ice, which is what we're after, it would be the water on the left divided by C for ice delta T plus LF plus C for water delta T. Okay, and the numbers that we would have for that, let's see what the mass of water was in this question. So we have 741 grams of ice, and we have how much water? Oh, sorry, 741 grams of water. We're trying to find how much ice. Okay. And we want to use the constants that they've given us. So we have, now you can leave it in grams here for the mass of water, because then the mass of ice will be grams. That's okay. So 741. And they tell you to use 4190 for the specific heat of water. And the delta T for that water was 70 minus 12. So that's 58. Okay, see if I can fit all this on the bottom here. C for ice, they give you in the problem 2000. Now you will see different numbers depending on the problem. Sometimes it's 2020, sometimes it's 2100, but this problem is telling us 2000. So 2000, and that ice is warming up 17 degrees. They give you the latent heat of fusion. I don't know why they don't put it in proper scientific notation. It's 3.34 times 10 to the 5 joules per kilogram. The C for water that they want you to use for this problem is 4190. And the change in temperature for the water is 0 to 12, so it's 12. Okay, if you put all those numbers in, you should get, and you should definitely check that answer, 430 grams. Okay, so that's how you do those problems.